Since it has been some time since we've studied second-order equations, it might be helpful to review our problem-solving process and walk through an example problem that we already did in lecture but should be familiar to you. So solving RLC circuits is very similar to solving first-order circuits in the sense that we find initial and final conditions, but there are additional steps that you have to determine whether a circuit is over or under or critically damped by examining the resonant frequency and the dampening coefficient. So these circuits follow a similar pattern, but they are much longer to solve and there are much more parameters that are needed. And as a special twist, because we have both inductors and capacitors in the circuit, we cannot simply rely just at the time before zero conditions. We must see how those conditions propagate to the time immediately after zero, as the currents across the capacitor and the voltages across the inductors can change instantaneously. So in these sets of videos, we will walk through an example problem-solving process for RLC circuits. Let's take a look at this example circuit. That is actually example number 6.2 in the book. In this circuit, we have voltage sources, current sources, resistors, capacitors, and inductors. And so because we have all three components of resistors, inductors, and capacitors, we have to apply second-order circuit analysis. And for this particular problem, the quantity of interest is this voltage across the capacitor, and this voltage will vary in time. And so the problem-solving process we're going to follow is the first part of this is we're going to look at what happens at time right before zero. And at time right before zero, we are going to assume that everything has been like that for a quote-unquote long time. And so our capacitors will become open circuits, and then our inductors will become short circuits. After solving for all of the voltages and currents throughout the circuit at time less than zero, we will then flip over and look at time just immediately after zero. And the reason for this is because there are voltages across those capacitors and currents through those inductors that don't necessarily go away. Those properties cannot change instantaneously. So once we flip over, those open circuits where the capacitors are will become voltage sources, and those short circuits where the currents are going to turn into current sources. So we will transform at time before zero. We will transform our objects into open circuits and short circuits. We will find the voltages across them and the currents through them. And then once we look immediately after zero, because those voltages and those currents cannot dissipate immediately, we replace them with equivalent voltage and current sources, do our analysis at time right after zero.